Hello, Professor. We could start.
Okay, thank you. Let's start. At the previous lecture, we finally established the classification of simple spherical varieties by colored cones. And the geometric meaning of the generators of a colored cone is that these vectors correspond to the b-stable prime divisors containing the closed G orbit on the respective simple spherical variety. The next lemma, which I already formulated at the end of the previous lecture, explains the geometric meaning of the intersection of the colored cone with the valuation cone. So this lemma, lemma 1, says that suppose we are given a vector in the valuation cone, non-zero vector in the valuation cone, and a simple spherical variety, or a simple embedding of a given spherical homogeneous space as usual, with a closed orbit Y. Then the following properties are equivalent. So the vector V belongs to the cone of this simple spherical variety if and only if the respective valuation is non-negative on regular functions over the canonical B chart intersecting the closed orbit. And this holds if and only if there exists a G equivariant morphism from the elementary embedding corresponding to this vector V, an embedding with a simple spherical variety with two orbits, the open one and the closed one of codimension 1, which is a divisor. So if and only if there exists a G equivariant map, say phi, from this elementary simple variety xv to x, sending the boundary divisor, the codimension 1 orbit. Well, let me say like this. I don't want to specify where the codimension 1 orbit gets under this map. I just want to say that there exists a G equivariant map from the elementary embedding corresponding to this vector V to X, extending the identity map on the open orbit. Exactly as I formulated at the end of the previous lecture. So the vectors of the valuation cone sitting in the cone of this simple variety X, sitting in this cone, are characterized as exactly those vectors for which an elementary embedding corresponding to this valuation, to this vector, possesses a map to X, to our given X, extending the identity map on the open orbits. Okay, so this is the statement. And now let's prove it. Let's first prove the implications from the left to the right. So in this direction, there are two equivalences, this one and this one. And let's prove both implications from the left to the right. So as for the first implication, I mean, we want to prove that if V belongs to this cone, then the valuation, the respective valuation, is non-negative on regular functions on the open B chart. So we shall prove it by contradiction, assuming the contrary. Suppose there exists a regular function on the open B chart on which the valuation v takes negative value, like this. Then, as usual, we can apply, since this function is regular on the open B chart, it has B-stable divisor of poles. And we may apply the second approximation lemma, as we often do. Which allows us to replace this function by a B semi-invariant function. So that this value is preserved under this replacement. So a given G invariant valuation takes the same value on F lambda as on F. And all other valuations corresponding to B-stable prime divisors may only increase their values. So those valuations which were non-negative on this function F, since F is regular on this open B chart, all valuations corresponding to divisors intersecting this B chart take non-negative values on F. And after this replacement, this property is preserved. The values may only increase. And this means that this function f lambda is still in this algebra of regular functions on the open B chart. So without loss of generality, we may assume that the initial function f was B semi-invariant. And this means, in the language of lattice vectors, this means that the vector v corresponding to the valuation, so this vector, I mean v, takes negative value. So its pairing with the weight lambda is negative. And for any other B-stable divisor intersecting this B chart, the pairing is non-negative. In other words, the pairing of lambda with any vector in the cone C sub y is non-negative. Because the cone C sub y is generated by all vectors corresponding to B-stable prime divisors intersecting the open B chart. So for any W in C sub y, this pairing is non-negative. So let me maybe illustrate it on the picture. So the picture looks somewhat like this. So we have this cone. This is my cone C sub y.
Well, Professor.
Yeah.
Which should we require that W is not equal to V?
Well, W is any vector. W, no, nothing. I mean, what is written here is just the reformulation of these properties. So the value of V and this function f.
But V belongs to the cone of the colored cone of Y.
Well, yes, this was our assumption, but now I want to draw it to a contradiction. And the contradiction is as follows. So we have we assumed that this doesn't hold. We assumed that this doesn't hold. So we found a function of this form satisfying this condition. Then we replace this function by a semi-invariant function with these conditions preserved. And now, if f is semi-invariant with eigenweight lambda, then these conditions are reformulated in this way. And what does it mean? What do these conditions mean? I am just drawing it on the picture. So what do these conditions mean? This condition means that this vector v, so we have a function lambda in the dual vector space. Lambda is a vector in the dual vector space. So this function is like this. I mean something. Let me draw it here. So this function lambda defines. Excuse me. This function lambda defines a hyperplane in the vector space where the cone CY lives. And this hyperplane is like this. So this will be lambda, this will be my lambda. Yeah, let it be here. So this bunch of inequalities means that the whole cone C sub y sits in a half space with respect to this hyperplane. So the so all vectors from this cone take non-negative pairing with lambda, while the vector v takes negative pairing with lambda, which means that this vector sits somewhere here in the other half space. So v, excuse me, let it be thinner. So v is somewhere here. And this is the contradiction, because you see, since the cone CY sits in a one half space, and the vector v sits in another half space, the vector v cannot belong to this cone. So this cannot hold. We assumed that this is not true, and we came to a conclusion that this cannot hold. So we obtained a contradiction. This is the argument for the first implication. As for the second implication, so now I want to prove that this implies this. I'll do it as follows. So the second implication. What do we have? So the identity map, anyway, the identity map on the open G orbit extends to a G equivariant rational map, maybe non-regular, but rational map from the elementary embedding containing this open orbit to the embedding X, to the simple embedding X. So we have a rational map from X V from xv to x. Let me denote this map again by phi. Excuse me. Extending the identity map on the open orbit. Extending the identity map on the open orbit. So I would say the picture is like this. So we have this xv xv in which we have two orbits. One orbit is the open one, y naught, and the other one is the divisor, the codimension one orbit, which I denote as dv. This is this guy. And we have also our initial variety, x. We have our x. And we have a rational map from here to here. This is without any extra conditions. This is all this holds. We have this map. Okay. Now we assume that this condition holds, that the valuation corresponding to this divisor dv, the valuation takes non-negative values on regular functions on the open B chart. So let me maybe draw the open B chart here. So it is somewhere here. Okay. Let me do it a bit better. Sorry.
Well, so
Yes.
the G equivariant map phi is a regular map or birational map.
No, it is birational. This dashed arrow always means that the map is birational. This is only birational so far. But I want to prove that in fact this map is regular. I want to prove this property.
I'm asking
But
the aim. So the aim is that phi is regular, right?
Yes, the aim is to prove that phi is regular. And now how I do it? Let me explain. So we have this condition. We have this condition. This means, let me turn to the next page. This means that for any regular function f on the canonical open B chart, on this open subset, so we have that the valuation v takes non-negative value on f. And this means that when we take the pullback of this function under the map phi, so we have this map phi, rational map phi, and we have a function here.
So this rational map is just an extension of the identity, or
exactly. This rational map is
Do this rational map is this rational map G invariant?
This rational map is G equivariant because it is the extension of the identity map on the open orbit, which is obviously G equivariant. So if we consider it as a rational map, it is more or less the same as this identity map, which is obviously G equivariant. So the map phi is also G equivariant. Since we have a function which is regular on here, its pullback under phi will be a rational function here, which will be regular on some open subset. So let me write it here. So the pullback of f will be regular on some open subset, depending on f, of course, u sub f in xv, intersecting, excuse me, the boundary divisor. This is because, well, let me try to draw it here. So we have an open subset in here. Let it be marked by red as well. Okay, we have an open subset in here on which the pullback of my function f from this set is defined, is regular, and this open subset intersects the boundary divisor. Why so? Because of this condition. Because of the condition that the value f takes non-negative value on the value v takes non-negative, the valuation v takes non-negative value on f. This means that the function f has no pole along this divisor. The function f has no pole along this divisor, and this in turn means that the domain of definition domain of regularity for this function intersects this divisor. Okay? Well, now if we apply this argument to any coordinate function on x sub y naught on this open B chart, so this is an affine variety, and its coordinate algebra is generated by finitely many coordinate functions. And if we apply this argument to any coordinate function, then we get an open subset, which is in the intersection of all these UFs for all coordinate functions. So we get an open subset on which phi is regular. Well, let me write it like this. So we have an open subset U in XV on which phi is regular. So this arrow is full, not dashed, a field arrow. And this open subset U maps under phi to the open B chart sitting in X. And this open subset U, so U is open, and this open subset U intersects the boundary divisor. Again, you just take for U the intersection of all UFs corresponding to the coordinate functions, on X, Y naught. Okay? So we have this U, let it be U now here, this open subset, which I indicated here, let it be U.
Why is the intersection of all UF open?
Because there are finitely many of them. Each of these UFs is open, and we take finitely many coordinate functions generating this algebra, yeah? And the intersection, okay?
So we require this.
Okay. So let's come back to this picture. So we have this open subset intersecting dv on which my map phi is regular. And since phi is equivariant, then this map phi is also regular on all g shifts of this open subset. So this implies that phi is regular on all g shifts of U for any g in my group. And this implies, in turn, that phi is regular on the whole of XV. Because there are only two orbits on XV, the open one and the closed one, this divisor of codimension 1, which means that U intersects both orbits, all orbits, and the g shifts of U cover the whole XV. So the regularity locus of phi is the whole XV, and we finally proved that phi is regular.
And so I want to ask a question. So why is the pullback regular? I think since phi is just a rational function.
So you mean this implication, yeah?
Yes.
Well, because of this condition. Because if phi star f were not regular, along D, so what is claimed? It is claimed that phi star f is regular on some open subset intersecting this divisor. Yeah, okay? If phi star f were not regular on any open subset intersecting this divisor, then phi star f would have a pole along this divisor. But this condition says,
Phi star f could have pole, but f can have no pole? Because I think
well, it is. I mean, it is the same function because this map phi just extends the identity map. So the fields of rational functions here and here are identified. You may you just consider rational functions in this field on different models of this field, on X or on this variety, but actually the fields of rational functions of these both varieties are identified.
I know now.
Okay.
And another question. So
yeah,
we have for any generator Fi, we have UFI intersects dV, right?
Right.
The next page.
Yeah.
And so why the intersection of all UF still intersects dV? I mean,
well, it is easy. It is easy because each of these intersections is an open subset in dV. Yeah. And dV is irreducible. dV is irreducible. When you intersect non-empty open subsets.
Yes.
You get it. Okay, good. So finally, we proved the implications from the left to the right, here and here. And then let's prove the reverse implications. This is even easier. So the reverse implications from the right to the left. Let's turn to this. So we argue as follows. So let's start with the property on the right, with this property. Suppose we have such a map. Suppose we have such a G-equivariant map, which maps the elementary embedding to X. Then the image of this divisor dV in XV is some orbit in X. Let me draw it here. So the image of dV under this map phi, which we assume to exist, is some orbit in X. Some orbit. Well, I don't want to indicate it to give a notation to this orbit. Some orbit in X. But all orbits in X contain the closed orbit Y in their closures. So the closures of all orbits in X contain the closed orbit Y. And this means that all orbits in X intersect the canonical open B chart. So the picture is exactly like this. So this orbit, the image of dV under the map phi, intersects the open B chart X, Y naught. Let me write it here. So the image of this divisor dV is an orbit in X, and the closure of this orbit, as I said, contains the closed orbit Y, which implies that the orbit itself, phi of dV, intersects the open B chart, which in turn implies that for any regular function on the open B chart, if you take the pullback of this function along phi, then the domain of this pullback intersects dV. So this function f, or its pullback, which is more or less the same, cannot have a pole. On this divisor dV. Let me come back to the picture. So it cannot have a pole here because the function f itself, its domain of definition, the regularity domain of this function, intersects the image of dV, intersects this. So this function is defined on some open piece of this orbit. And this means that its pullback is defined on some open piece of dV, which means that the valuation V takes, since there is no pole on dV, the valuation V takes a non-negative value on F, and we obtained this condition. Yeah, so we have proved that this implies this. And the last implication from here to here, well, what you do, you just take any semi-invariant function. So here you have taken any regular function on x, y naught. And now you may take a semi-invariant function, f lambda, which corresponds to the lattice vector lambda sitting in the dual cone for any lambda in cy check, a lattice vector in cy check. So if we take the function f lambda corresponding to this lambda, if you take this function, then since it is regular on this open B chart, we have these conditions for lambda. So lambda is in the dual cone, yeah? We have these pairings non-negative. But since V, for any, so since for any regular function on x, y naught, we have this inequality, if we take B semi-invariant functions for f, then we would have this inequality. For any lambda in the dual cone, we would have that the pairing of V with lambda is non-negative. And this condition exactly means that V is in the cone C sub y. So if for any lambda in the dual cone, the pairing of V with lambda is non-negative, this means that V sits in the dual of the dual, which is the initial cone. So we have finally proved that this property also holds.
I want to ask a question. So
yes, okay.
So why should we have the image of dv intersects x, y naught? I think x, y naught does not contain y. It just intersects y. Exactly.
What I say is that the image of dv is some orbit on x. So dv is an orbit, yeah? dv is an orbit of codimension 1 here.
Yes.
And its image is also an orbit in x, maybe of bigger codimension, but it is an orbit in x. And
yes.
I claim that the open B chart intersects all G orbits because it intersects the closed orbit. And all other G orbits contain the closed orbit in their closure. I guess that some time ago we already discussed this issue, that the open B chart...
I see.
Mm-hmm.
I think there is a discussion. I'm looking at my notes.
Yeah, because this is more or less topologically obvious. If we have an open subset intersecting something closed, then this open subset intersects anything which contains this closed orbit in its closure, just by topological arguments. So we have discussed it. Okay. So finally, we have proved this lemma. Let me put the end of proof sign. And this lemma, as I already said, gives us the geometric meaning of the intersection of the cone, which we associate to a simple embedding, the intersection of this cone with the evaluation cone, the geometric meaning for this intersection. Okay? Well, so we have dealt with simple embeddings of spherical homogeneous spaces, and now we turn to classification of general, not necessarily simple, spherical varieties. This is our next goal. So now, let me turn to the next page. From now on, let me denote by X any embedding of a given spherical homogeneous space Y naught. So Y naught is open in X, and X is an arbitrary, not necessarily simple, spherical G variety. Arbitrary spherical G variety. Okay. So we know that any spherical G variety contains finitely many G orbits. And to any of these G orbits, Y in X, we can associate the data which we considered already for simple spherical varieties. We can associate the set of valuations V over Y corresponding to all G-stable prime divisors containing Y. We can associate the set of colors containing Y. We can take the cone Cy generated by the vectors from the above sets. And we may consider the simple spherical variety, open subvariety X sub Y, which is the union of all orbits Y prime. Well, it is even a disjoint union because it is a union of orbits. Let me write it like this. Disjoint union of orbits Y prime containing Y in the closures. Or it is the same, well, yeah, I mean, no, it's okay. The union of all G orbits Y prime containing Y in the closure. It is an open subvariety in X. All this data. So we get a finite collection of simple open spherical subvarieties in X corresponding to all G orbits. And we get a finite collection of colored cones corresponding to these orbits, to these open simple subvarieties. So the next lemmas, which I'm going to formulate and prove now, describe certain properties of this finite collection of colored cones. So the second lemma explains how these cones are related if one orbit is contained in the closure of another one. So the lemma says that suppose we are given two G orbits, Y and Y prime.
Y prime is a G orbit, right?
Yes. Y prime is also a G orbit. So suppose you...
I mean the second to last line.
Yeah. Exactly. So Y prime is also a G orbit. By the letter Y, I always denote G orbits. So yeah, I didn't write it explicitly, but it is the case. Y prime is also a G orbit. So suppose we have two G orbits, Y and Y prime, such that Y is contained in the closure of Y prime. Then the cone C sub Y prime is a face of the cone C and the set of colors corresponding to y prime is exactly the set of all colors in D over y, a subset of colors corresponding to y, consisting exactly of those colors for which the respective vector Vd bar belongs to this face. So among all colors corresponding to this cone, we pick those for which the respective vectors sit on this face, and this will be exactly this set. So we may roughly, by abuse of notation, we can write it like this. By definition, we can write it like this. This is just the notation. The intersection of this dy, d over y, with the face cy prime. This is indeed abusing notation because dy is not a subset in the vector space in which the cones live. It is only mapped to this vector space, but still, I mean, the explicit meaning of this intersection is written here. So maybe I can illustrate what happens on the following picture. Let me try to draw a picture for you.
So cy prime is a face of cy.
Exactly.
Is this face closed?
Yeah, closed face. I mean, face in the sense of convex geometry. It is the intersection of the convex set of this cone with some supporting hyperplane. Yeah, it is closed face. Yes. So let me try to write to draw everything on the picture. So let's first this indicate the evaluation cone. In green, we have evaluation cone. Maybe like this. Excuse me. Try better. So this is the evaluation cone. Yeah, like this. And this is my V. Inside V, well, I mean, we have the cone C sub y, which is generated by some vectors. So C sub y is generated by vectors of two types. Some of these vectors belong to the evaluation cone. Well, like this maybe. And some other vectors are colors. So this is my cone. So yeah, I mean, let me try to express this as a kind of a cone. So you can imagine on the picture, you can imagine this as a kind of simplicial cone. C sub y. Yeah, this cone. So there are, as I said, there are two types of generators. Some of these generators are colors, maybe this one. So this is a color. And maybe this one also is a color. So let it be yellow. This is yet another color. And also maybe this one. Yeah, maybe this one also is a color. And for instance, this vector, this generating vector, is in the evaluation column. This is evaluation. So the picture is somewhat like this. And what is a face? A face is given by a supporting hyperplane. So you have some vector in the dual space, some linear function given by, you may assume that it is given by a lattice vector, say lambda. Let it be this one. This will be my lambda. Excuse me. This will be my lambda. And the face consists of all vectors in the cone C sub y perpendicular to lambda. Maybe let me indicate this face by yellow. For instance, this would be this face. Yeah, this would be this face. So this will be the cone C y prime. And the colors corresponding to this cone are exactly those colors for which the respective vectors sit in this face. So on the picture, the only color satisfying this condition is the blue one, this one. But in general, the picture can be more complicated, of course. So here is how all these things look like in terms of, well, in respect with the formulation of this lemma. Okay. Well, now I see that the first half of the lecture is almost over. So maybe it's a good idea to make a break now, not to stop the proof of this lemma, because the proof will take some time. So let's make a break, a 10 minutes break. And if you have questions, then I'm ready to answer as usual. So
Yes,
let's make a break. Yeah.
Sure. About algebraic group fraction. And is it true that if an algebraic group acting faithfully on a complete variety, then it has a fixed point.
No, if you this is true if you have a solvable group, if you have a connected solvable group, then this is a Borel fixed point theorem, the Borel fixed point theorem, which states that an action of a connected solvable algebraic group on a complete variety always has a fixed point. But if your group is not solvable, then of course it is not true. For instance, you may consider the projective space acted on by PGLN.
I see.
Okay. But for solvable groups, this is a very important theorem, actually. It has many applications. For solvable groups, it is true. For connected solvable groups. So you are welcome to pose more questions if you have. Well, if there are no more questions so far, then let me switch off my microphone. But if some questions will appear, just ask, and I will turn the microphone on again and answer. Okay.
Professor, sorry to bother you.
It's okay. It's okay. Mm-hmm.
So you say you just say that PGLN acts on the projective space, right?
Right. As an example, yeah.
So is the projective space in this case a spherical variety?
Oh, for the action of PGLN, yes. It is a particular example of a generalized flag variety. So the generalized flag variety is
a generalized flag variety. So is there a criterion to examine when is the open G orbit Y naught is already complete, so that no other variety can contain Y naught as an open.
Well, the criterion is exactly that. So the complete homogeneous varieties are exactly the generalized flag varieties. This, by the way, comes from the Borel fixed point theorem, because if you have a complete homogeneous G variety, yeah, then the Borel subgroup of G must have a fixed point on this variety. And this means that the stabilizer of this point is contained, that the stabilizer of this point contains the Borel subgroup. The stabilizer is a parabolic subgroup, which means that we have a generalized flag variety. Okay? So this is exactly the criterion. Generalized flag varieties are the only complete homogeneous varieties. Well, homogeneous under the action of linear algebraic groups. Of course, we have abelian varieties, which are also homogeneous and complete, but the abelian variety is not a linear algebraic group. It is a different thing. Okay, let's proceed with the proof of this lemma. So let's do the following. We choose a function which is regular on the open B chart intersecting the orbit y, on the open B chart in the open simple embedding corresponding to this orbit y, such that it does not vanish identically on y prime, and at the same time it vanishes identically on any B-stable prime divisor which contains y and not contains y prime. So recall that y prime contains y in its closure. So y prime is in a sense bigger than y. It contains y in its closure. And we are picking all B-stable prime divisors which are containing the smaller orbit, but do not contain the bigger orbit. So the picture, again, let me draw the picture. The picture is like this. So we have x. Recall that x is not necessarily simple, by the way. X is an arbitrary spherical variety. We have x. We have an orbit y, which is small. Let me just draw it as a small bullet, I would say, an orbit y. We have a bigger orbit, y prime, which contains y in its closure. We have the canonical B chart intersecting the smaller orbit. So let it be this. Excuse me. Like this. The canonical B chart intersecting the smaller orbit. X, Y, naught. And we consider all divisors, all B-stable prime divisors containing the smaller orbit, but not containing the bigger orbit. So these are my D's, like this. And since these D's do not contain y prime, we can pick a function which is regular on this affine open subvariety x, y naught, and which vanishes identically on all these divisors and does not vanish identically on here. Again, when one subvariety is not contained in another one, when one closed subvariety is not contained in another one, then there is no reverse inclusion for vanishing ideals, and we can find a function which which belongs to the vanishing ideal of one variety and does not belong to the vanishing ideal of another one. So this is what we do here. Okay. Now we can, as we usually did several times, we can, for instance, blow up the closure of y prime in X, and we obtain a map.
Hey, Professor.
Yes.
Why is such D exist? Or we do not need the existence?
I mean, let me say, if it does not exist, then there is no condition. Just we have if such D's do not exist, then we have no this condition. We have only this condition. No problem. I mean, but if such D exist, well, they should exist because these two orbits are different. And this means that the respective colors cones are different. and the colored cone is determined by the set of all b-stable prime divisors containing the given orbit. So they should exist, but actually in this argument it is even not essential. You just pick, okay?
Yes, I know.
Well, okay, yeah. So, by blowing up y prime, or the closure of y prime, is better to say, we can always find an elementary embedding xv, some xv, which maps onto x. So there exists an elementary embedding xv which maps onto x in such a way that the codimension 1 orbit, this divisor dv, maps to y prime. This can be obtained, for instance, by blow-up. What does it mean? Since the function f does not vanish, is defined and does not vanish along y prime, the pullback of this function under this map has no pole along dv. This implies that the value of v at this function f is non-negative. And also, the vector v belongs to the cone associated with y by the first lemma. By lemma 1. Because if this divisor dv maps to y prime, this means that the elementary embedding xv, its image, is actually contained in the simple open subvariety xy, because y prime, the image is contained in xy prime, because both orbits are in xy prime. The images of both orbits are in xy prime, and xy prime is contained in xy, because xy is the union of all orbits containing y in their closure, and xy prime so contains such orbits. So by lemma 1, this v is in this cone cy, and this condition also holds. Now again, by second approximation lemma, we may assume that f is semi-invariant, that it is a b semi-invariant function.
So I want to ask a question. How do we use lemma 1? Because the image is y prime and is
let me write in more details. So let me denote this map by phi, for instance, yeah. And then I claim that phi of xv is contained in xy prime, which in turn is contained in xy. Okay? And lemma 1 says that if you have such an elementary, such a map from xv to xy, yeah, if we have such a map from xv to xy, so xy is this x here in the lemma, then this means that v belongs to this cone. Okay, so since we have this, this implies this. Okay. Now let me repeat that by the second approximation lemma, we may assume that f is semi-invariant. Such that, so we replace f with a semi-invariant function, such that well, excuse me, I think that I wrote a wrong formula here. I said that let me elaborate on the value of v of,
Professor, so the image of dv is y prime or just inside y prime?
Yes. Well, it is an orbit. So it is an orbit. So the image of an orbit is the whole orbit. So the image is the whole y prime. It is inside y prime, and this implies that it is the whole y prime because it is a single orbit. Okay?
Yes.
Okay. So let me elaborate on this value, v of f. So since f does not vanish on y prime, does not vanish on here, then the pullback of f does not vanish on here identically. It is defined and does not vanish along this divisor. This means that f has neither zero nor pole along this divisor. And this means that this value is exactly zero, not just non-negative. It is exactly zero. Okay? And now we replace f. With a semi-invariant function by the second approximation lemma, such that this value is preserved, and the values of all other valuations corresponding to b-stable prime divisors may only increase. So they were non-negative on f. This means that f were regular on here. Yeah. And also they were positive. On these d's, because of this vanishing condition. And this condition will be preserved because the value of will only increase. The order of zero, the vanishing order, will only increase. So this lambda satisfies the following. Lambda is in the dual cone of Cy, because f lambda is a regular function on this open B chart. Also, its pairing with V is zero. Yeah. And the pairing of all other vectors corresponding to B-stable prime divisors, V lambda bar, Vd bar with lambda, is either zero or positive. It is positive for any B-stable divisor containing y and not containing y prime. For any B-stable divisor of this kind, it is positive because the function f vanishes on this divisor. Yeah. And for any B-stable divisor containing y prime, it is zero. For any divisor D containing y prime, it is zero because the function f does not vanish on y prime, and therefore it does not vanish on such a divisor containing y prime. So we have these conditions, and now let's look, what do these conditions mean? These conditions mean that the function lambda, the linear lambda, can be considered as a linear function on the vector space in which the cone C sub y sits. Yeah, this is a vector in the dual cone. This function lambda actually defines the supporting hyperplane. This function lambda defines the supporting hyperplane, like on the picture. It defines the supporting hyperplane, which contains all vectors corresponding to the valuations, corresponding to the divisors containing y prime. This means that the intersection of this supporting hyperplane with the cone Cy is exactly the cone Cy prime. Because, again, because this function lambda takes a zero value exactly on the vectors corresponding to the divisor containing y prime. So this implies, let me repeat that, this implies that Cy prime is exactly the set of all vectors in Cy on which lambda takes 0 value. Yeah. And dy prime, so the set of colors which contain not just b-stable divisors, but colors which are not g-stable, the set of colors containing y prime is exactly the set of colors in dy, such that the respective vectors belong to this phase. So this condition is satisfied. This means the intersection of dy with this phase in our notation. Okay. And also, let me make a remark. It is a side remark in the course of the proof. Remark.
Well,
Mm-hmm.
I have a question.
Yeah, go ahead.
So we prove that for b-stable divisor, the vanish of VD bar is equivalent to VD bar belongs to the column, right?
Say it again. You mean which? This one or this one? Which?
No. I mean, we prove that the vanishing of VD bar is equivalent to its to VD bar belongs to the colored cone. I mean, we proved this since
the vanishing of VD bar, this equality.
The vanishing of VD bar is equivalent to that VD bar belongs to CY prime. Yes.
Yes. Yes.
We prove this. But what about the other valuation that does not?
Well, the other valuations take positive values on lambda.
I mean the other valuation that does not come from b-stable divided by that comes from g-stable.
Well, g-stable implies b-stable because g is bigger than g. So when I write b-stable, I include g-stable in this set. So this includes also g-stable prime divisors. And when I consider only b-stable, but not g-stable divisors, I speak about colors. Colors is this set, yeah? But here I speak both about colors and about g-stable divisors. All of them are b-stable. So I include both things in this argument. So this argument says that this condition, vanishing of these pairings, picks exactly those b-stable divisors which are containing y prime. And these b-stable divisors.
So we use v lambda. The v lambda is 0 to determine that vd bar lambda is 0 for every d containing y prime, right?
I would say that you mean how to say? Well, I mean, so your question is where do we use this equality? Yeah.
Yes.
This is your question.
Incidentally, to the next equality for
this one.
No, I mean for the next one.
This one.
Yes.
Let me see. I would say we do not use directly this equality. We use the following here. We use this condition. We use the condition that f does not vanish on y prime. Well, f is f lambda. We use this condition that f lambda does not vanish on y prime.
I know.
But this condition is the same as this condition actually, because of this map. Okay.
I understand your process.
Okay, but by the way, let me also explain the meaning of this equality. So in fact, we can state that this V corresponding to the elementary embedding mapping to X such that the divisor dV maps onto Y prime. This V actually sits, this is a side remark along the proof, this V actually sits in the relative interior of the cone C Y prime. So let me turn back to the picture. In here, if you look at this picture, then you can say that V, the vector V, sits in the relative interior of this face, of this yellow face, somewhere here. Well, let it be somewhere here. Okay. This is this V. Why so? Let's look at what we have proved. So why V is in the relative interior of Cy prime? Indeed, for any, say, mu, the lattice vector in the dual cone, Cy prime, check. And for any B-stable prime divisor D containing Y prime, the vectors corresponding to these divisors generate the cone Cy prime, as we remember. So for any mu and for any such D, we have the following. If the pairing of V with mu is 0, then this means that F mu does not vanish identically on Y prime, which in turn means, since D contains Y prime, which means that F mu does not vanish identically on D. And this means that the pairing of V D bar with mu is also 0. So let me shift it to the left because I have no space here. Somewhere, yeah. Let me put it somewhere here. Is also 0. So we have this chain of implications. So for any mu in the dual cone, if this holds, this means exactly that this holds. So F mu does not vanish since the pullback of mu has neither 0 nor pole on here, then the function F mu does not vanish identically on here. And since it does not vanish identically on here, it does not vanish identically on all divisors containing Y prime. And this means again that the function F mu has neither 0 nor pole along such a divisor. This means this equality. So this mapping means that the vector V sits in the cone Cy prime by lemma 1. But also, if a vector in the dual cone vanishes on this V, it automatically vanishes on the whole cone, on all the generators of this cone. So if you have such a vector, so let's come back to this picture. If you have such a vector sitting in the cone, so this yellow cone Cy prime, such that any linear function which takes non-negative values on the whole cone and vanishes here would have take only 0 values on this cone. This means exactly that this vector is in the relative interior. Otherwise, we could find a supporting function for this vector. If this vector was sitting on some face of this cone, of this yellow cone, then we could find a supporting function which vanishes on V, but does not vanish identically on this cone. But here we proved that if such a function vanishes on V, it always vanishes on the whole cone for any D in this set. So this means exactly that V is in the relative interior. So this remark can be considered, can be viewed as an addition to lemma 1. Lemma 1 said that if you have such a map, then the vector V sits in the cone corresponding to the closed orbit in the simple embedding xy. But this remark is a more precise statement. It says that if such an embedding maps the boundary divisor exactly on the orbit y, then this means that the vector V is not just in this cone, it is in the relative interior of this cone. This is a more precise statement, and this will be useful for us. So let's memorize this remark. But anyway, we have proved the second lemma. We have proved that the cone corresponding to a bigger orbit is the face of the initial cone. So let me put the end of proof sign here. This lemma leads us to the following definition. So suppose we are given a colored cone. Let C, B be a colored cone. Then a colored face of the colored cone CB is the following. It is a colored cone, yet another colored cone, C prime, B prime, such that C prime is a face of C, and B prime, and B prime, excuse me, and B prime is exactly the set of those colors in B which map to this face. So in our notation, it is B intersect with C prime. So the previous lemma essentially says that if you have an orbit which contains another one in its closure, then the colored cone of this orbit is exactly a colored face of the colored cone of the smaller orbit. So the previous lemma can be reformulated shortly in terms of this definition, that passing to a bigger orbit containing the initial one in its closure is exactly taking a colored face of the initial colored cone. Okay. Now the third lemma says that any colored face of the colored cone of a G orbit corresponds to some bigger orbit. So lemma 3 says that for any colored face of the colored cone Cy d over y corresponds to some bigger G orbit. So the previous lemma said that for any bigger G orbit, its colored cone is a colored face of this one. And this lemma is the opposite statement, the reverse statement, that any colored face of this colored cone corresponds to some bigger orbit y prime. So the proof here is easy. Yes.
Correspond to some. Could we control the number of y prime?
Well, this correspondence is bijective. It cannot happen. It cannot happen that two different orbits correspond to one and the same colored cone because, well, because of the theorem we proved at the previous lecture that simple embeddings are in a one-to-one correspondence to colored cones. And if we had two different orbits corresponding to one and the same colored cone, then the respective simple open subvarieties in X would have one and the same colored cone. But this is impossible. Then they have to coincide. So the correspondence between orbits and their colored cones is bijective, because of the theorem on classification of simple spherical varieties. Okay? Well, so let's prove this lemma. So suppose we have a colored face. Say C prime, B prime. Suppose we have a colored face of CY. Yes.
I still doubt about the uniqueness since you prove that simple spherical varieties are in one-to-one correspondence to the colored cone, right?
Yes. Yes.
So if the variety X has two G orbits correspond to same colored face, then it means that there is a simple spherical variety that has two elementary embedding into X, right? But
you mean a simple spherical variety which has two different embeddings into X, yeah?
Yes. Why can this happen?
Because we consider embeddings which extend the identity map on the open orbit.
Oh, so the extension is unique.
Exactly. The extension is unique. If it exists, it is unique. Okay. But thank you for this question. Yeah, you specify some things which should be mentioned explicitly. So thank you for this for opportunity to make statements more precise. Okay, so suppose we have any colored face of this colored cone Cy dy. Let's take a vector. Since it is a colored face, it is a colored cone. And by the definition of colored cones, we have a vector. So pick a vector V, which sits in the relative interior of C prime, and which is a vector in the valuation cone. So this intersection is non-empty, as we know. The relative interior of any colored cone contains vectors from the valuation cone. And pick such a vector. And then, by lemma 1 and by the remark which we have just made in the proof of the previous lemma, we have a map from the elementary embedding xv to our xy, mapping the boundary divisor dv to some orbit y prime. Well, actually, by this is not by the remark we have made. This is just by lemma 1. This is by lemma 1. because we have a vector sitting in the relative interior of C prime, but C prime is a face of Cy. So vector V belongs to Cy. And since the vector V belongs to Cy, this means that we have such a map. Okay? And this map sends the boundary divisor dV to some G orbit in xy. To some G orbit in xy. Okay? And this implies, in turn, by the previous remark, which we have made at the end of the proof of lemma 2, by the remark which we have made, that this vector V belongs to the relative interior of Cy prime. We have this orbit y prime, the image of dV, and to this orbit there corresponds, by the previous lemma, there corresponds a colored face of this cone. And the vector V belongs to the relative interior of this colored face by the above remark, by the previous remark. So what do we have? We have two colored faces. We have two colored faces of this cone. One of these colored faces is this one, and the other one corresponds to the orbit y prime. And we have a vector which sits in the relative interior of both faces. So if we have two faces of a cone whose relative interiors intersect, then these faces should coincide. Hence, we have that Cy prime coincides with C prime. And this, of course, implies also,
I did not say why Cy prime belongs. Oh, because every relative interior of C prime it belongs to Cy prime. Right?
Not every. Just because we have two faces. So both, let me say, both these cones are faces of this cone.
Yes.
And when we have two different faces, then their relative interiors do not intersect.
Yes.
But here we have a common vector. This vector belongs both to this interior and to this interior.
So I mean that their relative interior are the same because we have this correspondence.
Well, just because if the faces are the same. The faces are the same because otherwise the relative interiors could not intersect, but they do intersect. They have one and the same vector in common.
This correspondence just means that the relative interior of C prime is contained in Cy prime, but not the other direction.
No, excuse me. Let me repeat again. If you have a cone, if you have a convex cone, and you have two different faces of this convex cone, then the relative interiors of these two different faces cannot intersect. Okay? It is just elementary.
Relative interior. Oh, I see. I was considered other content. Yes.
No. The relative interior. So this not sign means relative interior. So if these faces were different, then these two guys could not intersect, but they do intersect. They intersect in V at least. And this means that the faces should coincide. And also, since both faces are colored faces, so these sets B prime and dy prime are determined by these faces. This implies that these sets also coincide. So this implies that dy prime coincides with B prime because both of these sets of colors are obtained by this intersection construction. Both of these sets consist of exactly those colors whose respective vectors sit in this face, and the faces are the same. So this ends the proof of this lemma. we have proved that any colored face of the colored cone corresponding to an orbit also corresponds to some orbit, to some bigger orbit. So there is a one-to-one correspondence between colored faces of a given colored cone and all orbits containing the given orbit in their closures. Okay? Now comes the next lemma, lemma 4. Lemma 4, which explains the mutual position of two colored cones corresponding to two different orbits. Not necessarily contained one in the closure of another one, just two different orbits. So suppose y and y prime are two distinct g orbits in X. Then the relative interiors of the respective cones Cy naught and Cy prime naught, well, they may intersect, but they cannot intersect inside the evaluation cone. So this intersection is empty. So the relative interiors of the colored cones corresponding to different g orbits cannot intersect inside the evaluation cone. They may intersect outside the evaluation cone, but this intersection is empty. The proof is quite short. It relies on the previous properties, which we have already proved. So we argue by contradiction. Suppose we have a vector sitting in this intersection. So suppose we have a vector sitting in this intersection. Then we have the following picture. So we have a simple embedding. Well, let me maybe, I need some space. Let me put it somewhere below. So we have a simple embedding, an open simple embedding corresponding to the orbit y, the union of all orbits in X containing y in its closure. And since the vector v sits in the relative interior of the cone Cy, we have a map from the respective elementary embedding xv such that the boundary divisor dv maps onto y, sitting here. Okay? The image of dv is exactly y, because otherwise, if the image would be a different orbit in here, then by the remark in the proof of lemma 2, we would have that the respective vector v belongs to the face, belongs to the interior, to the relative interior of the face corresponding to this different orbit containing y in its closure. But since the vector v is in the relative interior of Cy, it does not belong to any face of Cy. This means that the image of dv under this map cannot belong, cannot be a bigger orbit. Okay, and the same picture holds for the second orbit y prime. Again, since v is in the relative interior of Cy prime, we have a map from this elementary embedding to xy prime such that dv maps onto y prime. Okay? But both this xy and xy prime, both these varieties are open subvarieties in X. So this guy is contained in X, and this guy also is contained in X. They are both open subvarieties in X. And therefore, we have two maps from XV to X. The first one given by this map, and then this inclusion. This map and this inclusion. And the second one given by this map and this inclusion. So we have, formally, we have two maps from XV to X. But both these maps are extending the identity map on the open orbit. And this extension is unique. So since this map is unique, if it exists, a map from XV to X extending the identity map on the open orbit. Since this map is unique, this implies that actually the image of the boundary divisor dV under this map is well defined. But this image is both y and y prime. So these two orbits should coincide. This implies that y coincides with y prime. And this ends the proof. So we have proved that if the relative interiors intersect inside V, then the orbits should coincide. If the orbits were distinct, then the relative interiors cannot intersect. Okay. So now we have seen, so let me remind you what we started with. Excuse me. Do it better. What we started with, we considered, not here, we considered a collection. We considered a collection of colored cones corresponding to all G orbits in my spherical variety X. So to any G orbit in X, we associated a colored cone. We have such a finite collection of colored cones associated with my spherical variety X. And we have proved several properties of this collection of cones. First, we have proved that if one orbit is contained in another one, then one cone is a face of another one. So maybe it's better to say that if one cone is contained in another one, then the colored cone corresponding, if one orbit is contained in the closure of another one, then the colored cones corresponding to these two orbits, one is the colored face of another one. This is proved in lemma 2, and lemma 3 says that any colored face occurs under this construction. And the fourth lemma says that if you are given two distinct orbits corresponding to two distinct colored cones in this finite collection, then the relative interiors of these colored cones, intersect, have empty intersection inside V. So these observations given by lemmas 2, 3, and 4 lead us to the following definition. So let me give the following definition. A definition of a colored fan. Colored fan. A colored fan is a finite collection of colored cones. Let me denote the colored fan by F. A colored fan is a finite collection of colored cones in my vector space E, spanned by the dual of the weight lattice, such that the following conditions are satisfied. First condition. If we have a colored cone in this set F, and we take any colored face of this colored cone CB, then this colored face again belongs to the set F. In other words, this finite collection of colored cones is closed under taking colored faces. This is the first condition. And the second condition is that if you have two distinct colored cones in this collection F, if they are distinct, then the relative interiors of the cones C and C prime have empty intersection inside V, inside the evaluation cone. So they may intersect, but only outside V. So if you have such a finite collection of colored cones satisfying these two conditions, so closed under taking colored faces, and with non-intersecting relative interiors, non-intersecting inside the evaluation cone, then we say that such a finite collection of colored cones is a colored fan in the vector space E. And the classification theorem, which I will formulate now and prove on the next lecture on Wednesday, says, so the classification theorem says that there is a one-to-one correspondence between simple not simple, between spherical varieties containing a given open orbit, containing a given homogeneous space, Y naught as the open orbit, spherical varieties with open orbit Y naught are in a one-to-one correspondence with colored fans in the vector space E. So while simple spherical varieties are in a one-to-one correspondence with colored cones, arbitrary spherical varieties are in a one-to-one correspondence with colored fans. Maybe I won't prove this theorem, but maybe the first thing to mention in the proof, which we can already do now. So starting with the proof of the theorem, only the first step of the proof, says that this correspondence is well defined. This correspondence is well defined. This means that, well, maybe let me say that the correspondence is given. The correspondence is given by associating to a spherical variety X the collection, let me denote it by F of X. It is the collection of all colored cones CY d over y corresponding to all g orbits in X. We have finitely many g orbits. To each of these g orbits, we can associate the colored cone. And the collection of all these colored cones is what I denote by f of X. And the first thing we can mention in the proof, and we'll stop on this point. The first thing in the proof is to observe that indeed this set f of X is a colored fan in the sense of the previous definition. So f of X is indeed a colored fan. This means that this set of colored cones is closed under taking colored faces, and the relative interiors of different colored cones in this collection do not intersect inside the evaluation cone. This stems directly from the lemmas which we have proven. Lemmas from 2 to 4. Because lemma 2 says that for any bigger orbit y prime containing y in its closure, the respective cone is a colored face of this one. Lemma 3 says that any colored face is obtained in this way. That this means that this collection of cones is closed under taking colored faces. This is this first condition. And lemma 4 says that relative interiors of different colored cones in this collection do not intersect, and this is exactly the second condition for the colored fan. So these lemmas in whole say that the collection of colored cones corresponding to all g orbits in X is indeed a colored fan. So this correspondence is well defined, and it remains to prove that it is bijective. This we shall do on Wednesday. Thank you for your attention, and let me stop now. If you have any questions, then go ahead. Any questions so far? So it seems that there are no questions so far. Let me again remind you that you can address your questions at any time by email. You have my email, and just write me at any time. I will try to answer promptly and try to answer all your questions. And also, let me remind you that I'm giving exercises from time to time, and I'm expecting you, at least those of you who need credits for this course, I'm expecting from you to send me solutions of the exercises. I think that for the last several lectures, we had a lot of theoretical material with just a few exercises, maybe a couple of them. But there were exercises previously on previous lectures, and you can still solve them and send me your solutions. And I think that we are close to finishing this big theoretical part concerning the classification of spherical varieties, and then we'll see examples, and also new exercises will appear soon. So I expect you to send me solutions to these exercises, to the previous exercises, and to those which will come soon. Okay, so still no questions so far? If not, then I'll stop sharing the whiteboard. And hope to see you all on Wednesday. See you. Bye-bye.